Hey YouTube, welcome back to the BladesIIB shop for another video. This week we're going to get into that Precision Matthews BS-1 dividing head. Hopefully you caught the last video. We had a little bit of fun unboxing that when it got delivered. If you didn't have a chance to see that video, you can check it out. I'll put the link in the description to this one. But in this video, we're really going to dig into that Precision Matthews BS-1 dividing head. We're going to strip it down, make sure it's clean on the inside, get it all back together, remove as much backlash as we possibly can, and then we're going to put that dividing head into operation. I've watched a couple of other videos on stripping them down, and typically they come with a lot of grit and grime left over in there from the manufacturing process. So that's what we're going to go in there and clean up and get rid of. I'm not going to spend a lot of time on all the steps involved in pulling this apart. I'm going to put that, my plan is right now pretty much fast forward the video and then just give you a look at these parts and give you a look at the inside on how clean or dirty it is. If you want a lot of detail on pulling this apart, I'm going to put a link in the description to the Bundy Bears shed video that I watched. And hey, no sense in repeating content on YouTube. He does a great job of walking through every detail and taking this apart. I plan to speed it up to get to that, and we're just going to take a look at it. So in addition to ripping it apart, we're going to make a couple of heavy-duty washers. I think in his video he makes a couple of other internal parts and he actually changes the bearings out. I don't plan to get that far into it. The bearings feel pretty good on this. So I'm going to make the heavy-duty washers. We'll knock those out really quick on the lathe, and then we'll get this back together. For a project, hey, we're going to make a couple of more chest pieces. We'll keep that theme going just because that I think making the rook or the castle chest piece on this one, it's going to give us a chance to cut some indentations. We're going to put 7 little indentations in there just because that's kind of an odd number, and we'll talk through that a little bit more when we get into the dividing head and making your calculations for the number of divisions that you want to make. But also had some feedback on making the pawn chest piece the last time, making that freehand and how that is not very repeatable. So making these 2 rook chest pieces today, we're going to talk through grinding your tooling and how you could set that up to actually make those repeatable even though we don't have a CNC machine. And our goal is to make 2 that are really close to the same, if not exactly the same. So that's going to be our goal with making the chest piece. So it should be a good opportunity to look at some custom ground tooling and just doing some oddball radiuses and some odd designs on a manual lathe and how you can get some repeatability out of that. So that's the goal for the project. First, let's go ahead and dig into this dividing head, do a little bit of cleanup, and just rip this apart and see what it looks like inside. So let's head over to the bench. So here we go with this dividing head. We're going to get this ripped apart, and again, I'm going to speed through this until I get to something to show you inside on how clean it is. But you want a lot more details on that, check out that Bundy Bears video, and again, I will put that link in the description to this one. Let's get this thing ripped apart. All right, pause there really quick. Definitely, pretty black and dirty in there. I think we can get that cleaned up a little bit. We'll do that. That's the reason we're taking it apart here. Has a good coat of grease. The grease part here doesn't look too bad. Just on the oil, there's lots of little bits. And then this little bushing, I know this is one of the parts that Bundy Bears made. I don't know that I have any brass oil light that size, so probably won't be remaking that piece. But the rest of this looks not too bad. Let's keep going. All right, we'll pause there. So it's not filthy in there, but it's pretty black and dirty, and I'm only about 10 minutes into taking this apart. So for the 10 or 15 minutes it will take you to pull this apart, I would definitely encourage you to do that. So again, they just all have this little bit of coat of black dirtiness on them. It's not filthy, But like I say, for the little bit of time it takes to pull this apart, I would encourage you to get in there and do that. We'll take a look at the inside here when we get it the rest of the way apart. But like I say, pretty straightforward. I'm only about 10, maybe 15 minutes real time in at the most here, and not long, not a big challenge to take this thing apart and get it taken care of. All right, that pulled out of there, and you can really see where on this one, yeah, we've really got some gear shavings, and we've really got some grit in there. Glad I pulled this apart. We'll get this all cleaned up. This is the optional bearing. If you wanted to get in there and put a Timken bearing or something in here, you can undo this collar, get these apart. I probably will still get this collar off just to be able to clean in behind it. There's no press fit there. I believe this gear is what's pressed on. So I should be able to just undo that collar, pull it off. If that gear doesn't just fall off of there, I'm not going to put it in the press and try to take it off. We'll leave the bearing in place, but we'll still be able to do a nice cleanup on this. Inside the case honestly isn't looking too bad. So it does look, inside there is looking pretty clean. We'll give it a little bit of a wipe out in there, but it really isn't looking too bad at all. So should just be some quick wipe down. We'll make 4 washers, 2 for this piece, 2 for the tailstock, and we'll get this all put back together. There we go, nice fit on that piece, but it does just pull out of there as well. There's a lock collar in there on the back of the housing. That's what clamps around the shaft and locks it when you're in place. It's got some holes on there. I could unbolt that and we can put the shaft in from the back to line that back up, but I don't think it looks that dirty, so I think I can clean what I need to with that in place, and we won't bother taking that back out of there. So let's get the rest of this cleaned up. That's pretty good. Instead of this being solid brass, they've got a steel collar that's threaded on the backside and it's just pinned to the piece of brass. So you've got brass on the inside to not mark it, but you are definitely threading onto a steel collar to keep those threads from stripping out of there. Good design feature, but yeah, all this stuff is just gritty, dirty. And these are those washers that we're going to replace. We're going to make a little bit heavier duty ones to stick on there. It's moving off of there. Yeah, it'll make it a lot easier to clean if I can bang that off of there the rest of the way. Well, that took a little more work than planned to get that the rest of the way off there. I finally just took it over to the anvil on my vise, a little more solid bench, stuck it on a flat piece of oak wood and banged on that since I don't have a press. And I wasn't really worried about getting it off of there since I didn't have a press. Once I got started, you just got to prove that you can do it. But honestly, I'm glad that I did. There are a couple of big metal chunks that came out of this gear. Obviously, I put some brass chunks in there trying to use my brass punch. But we will get that cleaned off, and that does allow me now to get this bearing off here and really make sure that we get this bearing all cleaned up, put back on there. So again, if you wanted to order a Timken bearing to replace it, you can get some bearing numbers off of this. It's a 32009X, so you'd be able to replace that bearing if you wanted to. I am not going to do that, but again, just looking in here at some of these pieces, we can definitely do a little bit of cleanup in behind here. Yeah, there's a little bit of a metal burr right there. Not that this goes fast, not that a couple of little metal chips are really going to cause huge problems, but worth taking apart and cleaning up since you can. So let me do a little bit of cleaning with some kerosene. We'll get that put all back together. Well, it's a nice day outside. We got the door open, so we'll use a little bit of kerosene solvent here and we'll get everything all cleaned up. Get that bearing in there first while our solvent's nice and clean. Same thing with our little thrust bearing. We'll get that in there while our solvent is nice and clean. Yeah, worth the cleanup, I'd say. Just a little nasty in there. Good use of our time. Let's get some fresh paper down and let's get this thing put back together. Well, we got some fresh paper down. Just flipped the paper, cleaned it up a little bit. Let's get all the rest of the parts over here and let's get this together. Now, they say you can put this together with just oil, no grease needed, and no reason not to believe that, but to me, just looking at some of the grease running out of these places, and I want some corrosion resistance, I can see this sitting for quite a while and not being used for a while. So I think I'm going to go ahead and put some grease in there as we put this together. Again, you can read, you can do what you like, and you may want to just put this together with only oil for yours, but that's up to you. And let's get one of these in place to lock it. I didn't make new washers yet, so we'll make those afterwards. Alright, so I cut it kind of short on my drill. I didn't go in quite far enough, so that's what you gotta love about a collet chuck, is even something that thin, I can turn it around, grab it, and we'll clean up the backside of that hole with the drill bit here. Well, that took a little longer than I thought it was going to. We had a few shop distractions, a couple other things going on, but still well worth the time and effort it went into that. I know I probably skipped through some parts as I fast forwarded that video. Just wanted to put together enough that you could see it coming apart, you could see it going back together, and see a little bit of what we did making the washers to go on there. So now we've got some heavy duty washers on where the center goes into place, and we've got some heavy duty washers put on where this bolts on. I think those work a little better than the original ones that were on there. And we've got the backlash out. So in the video, I will say it's a little bit finicky playing with backlash. We'll talk about that here in a moment, and I'll try to zoom in and show you what we ended up with. But bottom line, I definitely think it was worth a couple hours to go through and strip this apart. I did not put new bearings in there, but I can tell you that this feels significantly better now turning and operating than it did when it first came out of the box. And for sure, there's virtually no backlash left in it. And before, there was probably that much handle movement with backlash in there. Went together really nice, it feels good, and we definitely found some chips, some shavings in there. So if you buy one of these, not a Precision Matthews, any one I've seen online where these overseas dividing heads, just get in there, clean it up a little bit, and they're really a good feeling unit. It just takes an hour's worth of time investment to get in there and clean it up. So what are we going to do now? We're going to talk through a little bit about a dividing head, and if you haven't used one before, or if you have, we'll just quickly go through the pieces and parts and what came in the box. And then we're going to put it on a surface plate. They come with a nice hole in the side, and that is to set up your tailstock center if you want to. So we're going to get both of these on the surface plate. We're going to set the height of that tailstock because I plan to use both of them together, or that's what I plan to use that tailstock with. So we'll get that set up, and then after we have that set, then we'll bolt these feet on the bottom, since that's going to change the height, and I don't want to have those on there when I'm setting that center height. So we'll get center set up, we'll get these feet bolted on, and then it is essentially ready to go over there and put on the mill and put into operation. Let's talk a little bit about what came in the box. Obviously we had the dividing head, came with this height adjustable tailstock, came with these 4 feet, 2 to go on each of them to line those up in your T-slots on your mill. And it came with the dead center, so when the chuck's off, you can stick that directly in to the head, and then you can put this on. You mount this onto your dead center, you would clamp that in place. You can clamp some type of a dog around your piece with the tail on there, so if you needed the machine across a full shaft, you didn't want to be able to hold it in the chuck, you would be able to clamp your piece and to do that. I guess you're still going to be having a dog there, but regardless, if you wanted to be able to spin it on 2 centers and not have it clamped in the chuck, you would be able to do that with turning it between centers that way. It did not come with the actual dog to bolt onto a shaft to hook in there, so that was not in the package. That is something you'd probably have with your lathe, probably came with your lathe, so most likely you have one already. Didn't come with one here. And this came with your other set of jaws, so if you needed to hold something larger diameter, you could put these jaws on, and hold something larger diameter, you can hold that from the outside as well. These jaws, when they open up, you can hold something from the inside diameter around there. So if you want to hold some piece of pipe or something larger, you've got another set of jaws to be able to put on with that. Came with a thread protector, so if you take the chuck off, you can spin this onto the threads on there to make sure that if you are machining with that off, that you've got something on there protecting those threads for when you want to put the chuck back on. So it came with that, and of course it came with some additional dividing plates. Those are the accessories that came in the package. Let me zoom in on here and let's talk a little bit about the Backlash and getting that out. But before I zoom in and show you what we ended up with for Backlash, I know when this was apart and when you were watching me set it up, you were able to see this piece in behind the plate. Obviously that's on a cam, that's off center, and that is the main piece you're moving in there to twist that to push the worm gear up into the bottom, or to push the worm up into the bottom of the gear. That's the main piece for getting rid of the Backlash. And then this big screw on the back side here, this is putting pressure onto the back side of that shaft, and that's also taking up some of that Backlash by putting pressure on your worm and moving that around. And then there was a lock screw in the front here, and you can access that through one of these holes. So there is a lock screw there that locks this in place once you get that adjusted. Pretty finicky in there moving it around to adjust the Backlash. I will tell you that it was very little movement on that off-center piece on that cam. Just the slightest movement, and it would go from very, very tight to turn, more pressure, more tension turning that than what you would want, and just backing it off a little bit is where I got it to free run. And even still, it's a little bit smoother on probably 2/3 of it. It gets a little bit snug in 1/3, but I think I found the good compromise where, right there it gets really easy. That's really, really nice. And then it tightens up just a little bit in that 1/3 sort of an area. But again, I think I found a good compromise to where we've eliminated as much Backlash as possible, and we got that adjusted. There's also this thrust bearing on the back when I was putting it back together, and I went in and made sure that after I got this fairly snug, then that is when I checked this to see if that needed to go a little tighter, a little looser. And I basically tightened up this thrust washer on the back until it just kind of felt a little clicky, and then I backed that off until it was smooth and felt good again. Almost, like setting up wheel bearings on a car if you've done that. Similar concept in there to pull those two thrust bearings together. Bottom line, I've got it where it feels pretty good, and let me zoom in and I will show you what we ended up with here for Backlash elimination. I'm going to try to get it so you can see the plate on here and see the handle at the same time, and you can see that they're very, very much connected together. Alright, so hopefully that shows up on camera and you'll be able to see that this I am moving it right there. I'm moving, and if you focus in, you should be able to see that we're getting movement on that brass needle there. Let me zoom in even a little closer. I think you'll be able to get it. There, it looks like it's focused. And you can see just that little bit of movement, and we're getting movement on that needle. So if I try to hold this chuck, it's almost imperceptible the amount of Backlash we have. And before, when this was out of the box, it probably had that much Backlash. So clearly we have improved that, and we've got good back and forth. Regardless, no matter how little Backlash you get, you're always going to want to, when you are moving this, you want to keep it moving in one direction only, and you're going to want to creep up on that hole and drop it in a hole on your plate. You are never going to want to go past a hole and then back it up. If you go past a hole, then you're going to want to back it up a good half a turn and come back in and creep up on that hole again. You're always going to want to make sure that you stop that in forward motion in your hole and then lock it in place before you take your next cut. So regardless of how little Backlash you get, you're still going to operate with good Backlash procedures. And if you go past completely come back out, remove any backlash that may be there, then go back forward again and do that. All right, let's zoom back out. Let's talk a little bit about this dividing head. All right, so before we get this set up on center, let's just talk through the basic operation of a dividing head. When you use it, how you do some of the calculations for it. I think the why you use it is pretty obvious. If you're going to cut a gear, maybe you want to cut the spline on the end of a shaft, you need a perfectly even number of divisions around something. Even as simple as cutting the hex head on a bolt, you would use a dividing head. You would be able to index something, turn it a precise amount, take a cut, turn it another precise amount, take your cuts, and have those evenly spaced all around. That's the why. As for the how, there's 3 different ways you can do the calculations to come up with how you're going to use a dividing head. And I will talk about all 3 of those just using a couple of examples. So the 3 different types of indexing, you have direct indexing. So for direct indexing, you're going to use this plate that is right here. It has holes in it, and there is a tapered pin. Get that out of the hole. There's a tapered pin, and as you're spinning this around from the wheel, you're going to put a little bit of pressure on that pin, and it's going to drop into that taper, and it's going to push right in there. Now, with direct indexing, you are not counting the number of turns and the number of spaces, so back to that backlash piece, you really want to make sure you're going slow, letting that tapered pin drop in, and then you lock your head in place, and you take your cut. So direct indexing is right off of that plate. We'll come back and do a formula, do a calculation for that in just a moment. Then you have differential indexing. Differential indexing is where you're going to use the holes on the plate. You're going to actually count the number of turns, and you're going to do a calculation to figure out which hole plate you're going to use and where to drop your pin in there. And then you have angular indexing, and that is also going to be using the hole plate. Differential indexing is where your formula is going to be based on the gear reduction of your dividing head. So in this case, our gear reduction of this dividing head is 40 to 1. So we're going to do a calculation based on it takes 40 turns of the handle to make 1 complete revolution. So we're going to use that 40 to 1 ratio as our mathematical formula to figure out differential indexing. Angular indexing is just that. Maybe you know the angle of your piece. So instead of knowing that I want to cut 6 flats on here, that I want to cut a hex, maybe I know that I need to cut a flat every 60 degrees, which is actually the same, but maybe on your drawing it says 60 degrees. So then you want to be able to use a formula using the number of degrees instead of the number of indexes, so you can calculate how to do that using the angular measurement instead of the gear reduction. Sounds good when you say it fast. Let's go ahead and just talk through that with 2 different examples. The first example we're going to use is we're going to use 6, just like you were going to cut the hex on a bolt. If we wanted to cut 6 divisions and we wanted to use direct indexing on this hole plate on this dividing head, so on this ring right here on this dividing head, this is our direct indexing ring. It has 24 holes in it. So we can direct index anything that is divisible by 24. So if we look at that here, if we take our 24 holes, we divide that by 6, we come up with a nice even number, 4. If we wanted to do 6 divisions to cut a hex, we could direct index that. We would go to every 4th hole on that direct indexing plate, and that's going to work for 6 divisions. Direct indexing is going to work for us. If we want to do differential indexing, so again, for differential indexing, we're going to be using the gear reduction, the gear ratio of this dividing head to calculate that. The gear ratio on this dividing head is 40 to 1. So we're going to take that gear ratio and we're going to divide that by the number of divisions that we want to create. Although we need to come up with fractions, sometimes you can use a calculator just to check your math and make sure it's working right. So if we just do the calculator division, that comes out to 6.666. If you're quick enough and you do fractions enough, you can already identify that 666 is 2/3. But we can still reduce this fraction. So 40 over 6, 6 times 6 is 36. That leaves 4 left over. So 6 and 4/6 is the number of turns, or that reduces down to 6 and 2/3. So then we would need to find a hole plate. We would need to find one of these whole circles where you can divide it by 3 so that you can do 2/3. So something like 27. 27 is divisible by 3, and you could do 6 turns and 18 holes on a 27 hole circle would get you 2/3 of the way around. What other numbers? I have a whole circle that's 15. So you could also do 6 turns, and you could do 10 holes on that 15 hole circle. 15 is going to get you 2/3 of the way around. 18 is another hole circle available. So you could do 6 turns, and you could do 12 holes on the 18 hole circle. So once you have that figured out that it's 6 2/3, you have a couple of different options on which hole circle to use, which plate. So those other numbers I was calculating were off of a different plate. Looking at the plate that I currently have on here, I've got 37, 39, 41, 43, 47, and 49. So with this particular hole plate that's on here, only this 39 circle, the second circle in from out from the inside, that would be 26 holes on a 39 hole circle would get 2/3 of the way around for me. So I could use this plate that's on here. I could go 6 turns, and then I would go 26 holes on that 39 hole circle for the other 2/3 of the way around. So that is what we would do if we were doing differential indexing. Now, sticking with the same numbers, so we don't want to change the numbers. I just want to show you how this formula works exactly the same, no matter what number of divisions you're using. So now, if we wanted to do angular indexing, we'll go with 6 divisions again. But to figure out what 6 divisions is as angular would be 360 divided by 6, and that lets you know that every division is 60 degrees. Now, we're assuming that our print told us that it was 60 degrees. So we now have 60 degrees. So how do we figure out angular indexing? Before we can do our angular indexing formula, you first need to make sure you understand how many degrees per revolution your dividing head functions. So you're going to have to do this calculation one time, and then this is going to be a standard that you will use for any future angular calculation. We know that our dividing head goes 40 turns per revolution, so we know that it's a 40-to-1 ratio. So we just need to figure out how many degrees does our dividing head go with every revolution. So if we take, again, 360 degrees to go all the way around, divide that by 40 cranks to go all the way around, and that means that every 1 turn on our handle is going to take us 9 degrees. So now we have a standard for this dividing head. Anytime I'm going to do angular indexing with this dividing head, I'm always going to use that number 9 as my constant. So now let's go back to what's the formula. Before we were using 40-to-1 for differential indexing. Now our formula is going to be the number of degrees that I want to cut divided by the number of degrees per revolution. So in this case, we want to cut 60 degrees. Our dividing head goes 9 degrees per revolution. Pull out my calculator again, and we're back to that is 6.666. So you can do your calculation both ways just to help you verify if you're doing an important piece and you like to double check your work. We can also then reduce that fraction down. 60 over 9. 9 times 6 is going to give us 54. That leaves 6 left over, so that's going to be 6 6/9, which again reduces down to our 6 2/3, exactly like what we had up here if we did our formula using differential indexing. The different types of indexing aren't going to give you a different answer. They are just 3 different ways to come to the same options that you have for your dividing head, whichever is going to be easiest. Now in this case, all 3 of these examples worked, and they got us to a good resolution, a good answer. We could use any one of these 3 options to get there relatively easy. Let's look at one more example. Doesn't necessarily work, and this is where you may, depending on the numbers and the fraction, you may want to calculate it using one of the different formulas just to make it easier for you. Let's talk about 7 divisions, and 7 divisions is actually what we're going to use on our chess piece, our project that we're going to make, just because I wanted to pick something that direct indexing didn't work for. In this case, we're going to take our direct indexing formula, which is our number of holes on that direct indexing plate of 27. We're going to divide that by 7, and you come up with 3.428. We can't stop and put a pin in partway between holes. If that's not a perfectly whole number, direct indexing is not going to work for us. All right, so we figured out that direct indexing is not going to work for our 7 divisions. So let's move on to differential indexing. So if we do differential indexing, then we have our 40 gear reduction of our head, 40 over 7, the number of divisions we want to do. And we can pull out a calculator. 5.7142 is what that equals. I can't do fractions well enough to figure out exactly what that is, so we'll have to go back to reducing our fractions, which this one pretty easy. 7 times 5 is 35. So that leaves 5 left over. 5 and 5 over 7 is what we're going to need for our number of turns. So 5 full turns and 5/7 of a revolution. So we need to find a bolt hole circle that is divisible by 7. And what we have divisible by 7 is 49. 49 is going to be divisible by 7. So we're going to need to go 35 of 49 holes is going to be 5/7 of the way around. So since that's actually what we're going to use for our project, let's take a minute right now and go ahead and set up our dividing head for that. So to set this up, we're going to set our little markers on here, and these are going to help us get that in the same spot every time without having to count holes. We're going to count holes once, and then we shouldn't have to count holes again after that. So if we are in that first hole right there, so we would not count that one, and we would count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35. Let me find the screw to tighten that back up. So we got that tightened up. Now I want to double check and just make sure. So since we know we're doing 5/7, there's a lot of holes to count 35. I'm going to mark where I finished off on that hole, and I want to count around to, this is where I would have been in my pin. So I know I started on the numbered line on the holes. So I should have, where I left off, I should have 14 holes around to that, since that's 2/7 that were remaining. To double check that I did a proper count, I can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So I've got 14 holes. So I feel confident that I have those spaced appropriately. Now, wherever I finish my hole, move your dividing head, and we would be going 1, 2, 3, 4, 5, and we'll come around to our 5/7. I want to let that start, drop in where I don't have any backlash, and then I immediately want to move my spacers, and I would lock that in place, make my cut, come back and do that again. So that is differential indexing, and that worked for us for 7 spaces. Let's just quickly talk through that exact same formula now for angular indexing. So now we want to do 360 degrees divided by our 7 spaces. That's kind of a crazy number of 51.4285. So already it's looking like, wow, this isn't going to be very user-friendly for fractions. But let's continue on the journey. We already know that our standard for our dividing head is 9. We calculated that before, so it's still 9. So we need the degrees to cut divided by degrees per revolution of our dividing head. So we want to cut 51.4285 degrees divided by 9. That does divide out on a calculator to 5.7142, and you can see that that is exactly the same number as we had using our differential indexing formula. But the bottom line is 51.4285 over 9. To try to put that into a fraction that is going to be usable, a lot more challenging if you're good enough with fractions to be able to do that. So let's see, 9 into, that would be 45 and 6.4285 remainder. Again, very challenging to put that into the lowest common denominator to get that out to 5/7. So I would consider that angular indexing really does not work for that one, and differential indexing is what I would use to calculate out my number of turns of the dividing head. Hopefully that helps you understand just by using a consistent formula across all 3 of those, and helping you understand why, when you may want to use one formula over the other formula. You're just trying to get numbers that are simple to work with, because you want to reduce errors, eliminate errors ideally, and keeping the number simple is what's going to help with that. So we now have this set up for our 7 divisions. That's going to be good for when we get to our project. We won't have to go through that part again. Let's quickly get this set up where our tailstock is on center. I don't plan on using the center for this project. We're not going to need that sort of support for the little chest piece that we're going to do. But I want to make sure I get that center set up before I go through and put these feet on the bottom, and it's not going to sit level on my surface plate. Let's go ahead and get the cover off of this surface plate. We'll get that pulled over here on the bench, and we'll very gently set these 2 heavy pieces up on the surface plate, and we will get that center lined up in there. Okay, just did a quick level adjustment on my surface plate on here to make sure that when I can put my level across the top of that, when I bolt that down, since it has 2 bolts, we'll get that close so it's right off on one line. So that'll give me a good measurement, good marker on there that I'll be able to duplicate when we tighten that back up on getting that centered. There's a little bit of variation as I lean on the table over here, but I would say that that is pretty darn close. I feel like our dividing head is set up. We are centered in there, ready for operation. Let's get our feet bolted on the bottom. Let's get that done. And if you don't have a surface plate for that step, you can always just put it on your mill table. That's probably going to be your next flattest surface that you have. Set them both on your mill table, and you can set up the center that way. snug fit in there. They have to scrape a little bit of paint away. Perfect. Popped right in there now. Let's get this over on the mill. Definitely takes up some real estate on here, so we're going to pull it down and have it back off of this end of the table so that we're still essentially milling somewhere in there close to the middle of the table. So I've got a couple of shortened studs that I modified for holding my vise down and making sure I can still swivel my vise. I had to use one of those to get clearance under the chuck. This is the standard height that came with my clamping setup, so I've already machined and ground a couple of those down. So that worked for the headstock, and these tall ones should work for the tailstock. So you can see that with our little feet on the bottom, that holds them pretty straight. I'm hoping that if I push that pressure to the back, but we'll run a dial on there and we'll get a sense of how straight it is. For the part we're machining today, we could be off by quite a bit for just putting a little groove in the end. Obviously, if you're doing a longer part, you're going to make sure you put a dial on your long part and make sure you get this all dialed in nice and square and don't just trust the little pieces on the bottom. But for what we're doing today, that's great. But once I do get it clamped down, we'll run a dial on there just to see how square it did come out. Probably just run it down the back side of this face over here and we'll see how square that is on there just without anything other than just using those self-centering feet on the bottom. And that's what it would look like with the tailstock. We're not going to use the tailstock today, so I'm not going to clamp that on. Just wanted to see the T-nuts run into those little feet on the bottom, but they still get on there far enough that you would definitely be able to clamp that down the way it is. So for future reference, I know that I have all the clamping and everything that I need to get that tailstock on there. For today's job, we don't need it. So we'll pull that back off and we'll just get the headstock clamped down. Well, that was across about 5 inches or so of it back there. So across 5 inches, barely moved a tenth. So I would say we got that locked on there pretty square, and that is just using those self-centering feet that it came with and pushing those all the way up against one edge of the T-slot. Pretty good repeatability, I think, to slap that on your mill table and get that on there. Well, I am pretty happy with that. We've got that locked on there. Tell you what, while we've got the dial out and we're just checking this, let's go ahead and check out what the runout's like on this chuck. So let me throw a piece of steel in that chuck and we're going to check the runout on it. We'll do that while we've got it set up. All right, I've got one of these little spacers that I had for the grinder, so I know that these two surfaces were turned together, so these should be nice and concentric. So we'll grab onto the flange and our 3-jaw, we'll be able to put our dial on the outside of that step. Make sure that, yes, that is going to have enough clearance around our chuck there. Mark our jaws there real quick and see those coming around. Let's get in where we can see that dial a little better. Not bad, right about 1 thou runout on there. So we used our self-centering feet. We got this on our table and it came out within about a tenth of being squared up on our table. We put a dial on the outside of a piece in that chuck and it's within a thou. I would say for a 3-jaw chuck, a dividing head, I feel pretty confident I can just slap this onto my mill anytime that I want it, and it is basically set up and ready to run. Very happy with how that's turning out. All right, a couple other things I want to check as we are reviewing this index head is we checked what the runout is on the chuck with something in the chuck, but I want to go ahead and check the runout of this chuck all by itself. So let's zoom in on the dial there so you can see what's happening. All right, we got a little dot where we're going to start. Let's get that around one time. So we've got about 2 thou runout on the outside of the chuck. We only had about a thou runout on something actually held in the chuck. Definitely what we're holding in the chuck is as accurate as what the chuck is mounted on this device in general. So that is looking good. And the other piece we need to do is we didn't check the runout across the surface to make sure that we had this level. I just marked it, I zeroed it based on the little gauge on the side, but that gauge is not super accurate. So we do need to make sure that we run the dial across the front of this or across the top of this to make sure that we have it sitting in there actually at 0 degrees. So I'm going to check that really quick. All right, so we are about 15 thou low on the front there. So we're about 15 thou low in just that few inches. So we need to lift the front of this up a little bit. What I'm going to do for that is actually have one of these little 1-inch screw jacks that we made on another project. So I'm going to put that underneath, tighten that up, and that way when I loosen those bolts, it's not just going to fall all the way forward. And we will use the screw jack and we will lift that up until we get that pretty close to zero. I'm trying to think, it's a long ways if we want to split the difference. Don't think it's really going to take the back down very far. So we'll go up almost that full 15 thou and we'll see what that does for us for dialing that in. Okay, so the screw jack worked. I loosened that. It didn't come down at all. Just a little bit off on width. Let me find something I can set that screw jack on. I'm just going to run it once without even tightening it just to see how close that is. So it's raising the front, but it's raising the back a little bit as well. That is closer. That's got us within just a couple. That's within about half a thou. Let me tighten that up and see if that holds. Well, it's over. I think we can get better than that. That's almost a thou in just that short distance. Let's see if we can't get it just a little better than that. Okay, so our screw jack has been working. Let's check our run out there across the top of that. I think we can call that good. That's within about 1/10, maybe 2/10 at the most. Well, now I feel like we have this in here and we have this accurately set up. Get our screw jack out from under there. So all in all, very happy with the quality on how this turned out. If I had to call out one weak part on this whole unit, I would say it's this locking screw that we have in here. And only because you've got all this diameter and yet they put just this little thread in there. So again, that's what's going into the collar inside here to lock it when you're taking a cut. And you're going to tighten that up to keep this from having any turning, any movement on it. I think that thread could have been a little bigger and just giving that a little more oomph as you're locking it down. You get in there and you screw that, and it just feels like if you crank that too hard, you'd be able to strip that out or break something. So if I had to call out one weak part on the whole unit, I would say that that's it. But otherwise, really happy with the quality on this, and I think it's going to last a lot of years out here in the shop, so it should be good. Well, now that we've got this fully checked out, we've checked the run out on the outside, checked the run out in the chuck, made sure we've got it dialed in on our table, and it is ready to go. Now we're ready to head over to the lathe and make some chips and knock out these chest pieces, or at least head over to the lathe, talk about that project, and start sharpening up some tool bits. So let's head on over to the lathe. Well, YouTube, I'm going to head over to the lathe and start working on that part, and that's going to end up being part 2 of the video. You saw at the beginning of this, I dropped in a slide where the video was just getting too long. I needed to break it up into 2 parts. So we're going to call this the finish of part 1. We've gone through this complete dividing head. We've disassembled it, cleaned it up. We got it back together. We talked through all the ins and outs of how to use it. We've got it mounted on the mill and ready to go. Dialed it in, checked how accurate and how amazing this dividing head is. So that is a good place to wrap up part 1 of the video, and you're going to want to tune back in for part 2. That is when we're going to spend some time making those chest pieces and actually putting this dividing head into operation. Since we're not going to be so rushed now to get all of that done, we'll spend a little bit of time in talking through how to make those chest pieces, how to go through. We're going to take and grind up some tooling to make sure that we have ability to repeat that, get those radiuses and everything on those chest pieces set up. And we're going to have time now that we need to go through, and we needed to cut a hex on these little screw jacks we made a couple of videos ago as well, so that when you're trying to turn those like I was doing to adjust the height of that dividing head on the table, it would have been really nice if I could put a wrench on there instead of trying to just hold that with my fingers and turn that screw jack. So that reminded me we need to cut the hex on these as well. Tune in for part 2 of this video, and we're going to go through all of those pieces and parts. If you want to know exactly when that gets released, hit that subscribe button, ring the bell, you'll know when the video comes out. But essentially look for that next Saturday morning at 7 a.m. You can have your first cup of coffee getting ready to go out to your shop, and you can watch part 2 of this video and see what was taking place in the BladesIIB shop the week before. Also, look for a midweek drop-in video. I've got a customer project here. If you look back at the video making the hubs, the customer brought in, he finally got some other pieces, and the wheel studs on those are going to be 1/4 of an inch too long. So we're going to talk through how do you hold an odd-shaped piece in the lathe, and how am I going to grab those studs and turn them down 1/4 of an inch shorter and get those ready for him. Tune in for that midweek, but until then, hey, as always, I sure appreciate you watching the video, appreciate all the comments that are coming through, and I hope you're out in your own shop making some chips of your own, and we'll look forward to catching up with you soon. Take care.